I had a request to work out a few of these. So here I go. I know some of you are having a little trouble with the math in chapter 3. It could be definitely a little tricky, especially since they throw in a ton of material in chapter 3. So let me give you these extra questions to kind of review. Okay, the first one was number 7. This was definitely a harder one, and that's why I had it include a tutorial. And this is one of the try to find the molecular formula. So when you have a hydrocarbon, it's a little bit different. You can follow the tutorial. And let me kind of follow it, here your strategy, and show you how that would work out. So the question says you have a complete combustion of 4.6 grams hydrocarbon produce 13.9 grams of CO2 and 7.13 grams of water. Now, if you're wondering why that doesn't add up, that I have 4.6 grams of hydrocarbon, and whenever I combusted it, it created 13.9 grams of CO2 and 7.13 grams of H2O, and where that doesn't, they should be equal. Well, it's not considering the oxygen. Whenever it combust, the definition of that means you react with oxygen. So that missing mass, since this is only 4.6, the remaining that adds up here is from oxygen. Anyway, they weren't very clear on that. I want to make sure you know that. It's not important for the problem, it's just more important for understanding. Okay, so we need to find the empirical formula. We need to find what is this hydrocarbon, okay? Here, and this is the data I'm going to use right here, 13.9 and 7.13. A hydrocarbon, as you see here, is made up of carbon and hydrogen, okay? Hydro meaning hydrogen, carbon meaning carbon, okay? So the first thing we need to do is find the moles of C, the moles of H, and then do our regular empirical formula calculations. Okay, so the hardest part, I guess, is getting the moles of carbon, hydrogen. Okay, so you get your moles of carbon through the amount of CO2. So I'm going to put on here. Okay, for carbon calculation, I have 13.9 grams of CO2. Okay, this is how you calculate the carbon, because we can either use CO2 or H2O. Notice H2O has no carbon in it, so I can't figure out how much carbon is in the product. Okay, so all the carbon in the product comes from CO2. So I need to calculate this into moles of carbon. Put up here so I know my end goal. So anytime you're trying to go from gram of something to mole of something else, so notice that CO2 is not just carbon, okay? Carbon is not just CO2. So I need to convert this to moles. So I calculate what's the molecular weight of CO2. Carbon is 12 on the periodic table. Oxygen is 16 on the periodic table, but there's 2 of them. So when I add those together, it's 44. So CO2 adds up to 44 grams per 1 mole of CO2. Okay, now to get to moles of carbon. I'm trying to get to moles of carbon. Okay, for every 1 CO2 mole, so the CO2 moles will cancel out. This is called a mole-to-mole ratio. See, a mole to mole, and we're doing a ratio here. And that's how you get to a mole of something else, always a mole-to-mole ratio. Okay, so there's 1 carbon per every CO2, because you see the formula CO2, notice there's 1 carbon in there. If I would have asked about oxygen, there would be 2 oxygen. Okay, there's 1 carbon, so there's 1. So now I multiply this all out and I'll get moles of carbon. So 13.9 divided by 44, and I'm going to get 0.316 moles of carbon. Okay? Now let's look at hydrogen. Now watch this. We're going to do it exactly the same setup. Anytime, again, you go from gram of one thing to a mole or a gram of something else, you do the same setup. Okay? But now I'm going to use H2O because that's where the hydrogen is at. Let's see, there is 7.13 grams of water. Water, oxygen is 16, hydrogen weighs 1, but there's 2 of them, so that's 18 grams per mole. So right on here, there's 18 grams of water per 1 mole of water. That's the molecular weight. Notice the same thing I did up here. I started off with my grams of CO2, and then I used the molecular weight. So then the next step, I'll be using the mole ratio. Okay? For every 1 mole of water, how many hydrogens are in there? 2. There's 2 hydrogens per every 1 mole of water. So think of moles like 1 molecule. So for every 1 molecule of water, there are 2 hydrogens in there. So 2 hydrogen moles. So then I'm going to multiply this out. I have 7.13 times 2, all divided by 18, which gives me 0.792 moles. Okay, now let me make a little room here. Change the color. Let's do the next step of the problem. Okay, so this is step 1 and 2 of the tutorial. Okay, now we know how many moles. Now we need to get the ratio. So remember when we calculated the empirical formula in chapter 3, we converted everything to moles. So we have 0.316 moles of carbon and 0.792 moles of hydrogen. Now remember, this is where we divide by our lowest amount of moles, and that would be carbon. So 0.316, 0.316. Here we get 1, and then when you divide 0.792 by 3.16, you get 2.5. Well, when we're doing ratios here, we need whole numbers. Okay, that's how we're going to get the empirical formula. So how can I convert 2.5 to a whole number? What's the shortest way? That's if you multiply it by 2. If I multiply this by 2, I have to multiply this one by 2. Okay, so it gives me 2, and 2.5 times 2 is 5. Now I have whole numbers. So basically, or I'll give a review here in a minute. This gives me the empirical formula since they're both whole numbers now, C2H5. So let's review the steps. The first thing is we converted it to moles. And that's what we do for any empirical formula. Normally, though, they give you a percent or they'll just give you the grams. And we got the grams, but it wasn't a direct. They gave us CO2 and H2O, so they didn't give us exactly how many grams of hydrogen or how many grams of carbon. We had to calculate that. So first we convert our carbon, our CO2 to carbon moles, and our hydrogen, our water to hydrogen moles. Okay, so first we get the moles of everything. Then once we get the moles, we divide it by the lowest number of moles we calculated. In this case, carbon with 3.16 or 0.316. And then when you divided it out, we didn't get whole numbers. Whole numbers meaning not fractions. So we had to multiply it, both numbers, to get your whole numbers for our ratio, which is C2H5. This is the ratio. The ratio is 1 to 2.5, but we don't put on there we have 2.5 carbons. We have to have whole numbers of carbons, so that's why we get 2 and 5. Okay, so this was definitely a more challenging question. That's why I have it on the homework and not on the exam. I wouldn't have one this long. On the exam, it would have probably given you the moles right here, the moles of carbon and hydrogen directly. But this is a good review. This is how you see it in real life. Okay, so now let's look at the next question, 8. This one deals with molarity. Yeah, this is in chapter 3. This is the very end of chapter 3. I'm just going to do one of these. I'm going to do the harder one, which is B. Okay, so 23.1 grams of magnesium sulfate in 937 milliliter solution. And this one is 0.8 moles of magnesium sulfide, and this is sodium sulfide in 1.05 liters. Okay, I'll set this one up, but I'll actually calculate this one. Okay, so first you need to know the definition of molarity. Molarity equals to moles of solute over liters of solution. Okay, let me just set up A for you really quick. A, I don't remember what the numbers were. 0.8 moles and 1.05 liters. Gave you 0.8 moles of solute and, oh, now I don't know the liters again. 1.05. Okay, so you have your moles of solute, liters of solution, just plug it into that formula. Okay, B is a little bit harder because there are a little bit more calculations you have to do. So that's why I'm going to show you this one. This one, they give you 7.13 grams, or not 7, we'll give you the wrong problem. 23.1. Just erase it. .1 grams of magnesium sulfide and 937 milliliters. Okay, so this is still our formula. That hasn't changed. So this is our solute. This is our solution. Okay, and so we need this solute to be in moles, not grams. So this is just a gram to mole calculation I need to do here, just so I can put it in the correct units for my formula. Okay, so 23.1 grams of magnesium sulfide. So if I add up, magnesium sulfide on the periodic table to get the molecular weight, you're going to get 56.4. Let me know if you can't figure that one out. I can email you and show you. Okay, per 1 mole. Okay, so if we do this calculation, 23.1 divided by 56.4, we're going to get 0.41 moles of magnesium sulfide. Okay, so now we have our moles. Great. Okay, let me change your color. Now we don't want milliliters, we want liters. So we just do a milliliter to liter conversion here. There are 1,000 milliliters per 1 liter. So that gives us 0.937 liters. So great. I have my correct units. I have moles now and I have liters. So all I need to do is plug it into my formula to get the answer, which is going to be 0.41 divided by 0.937, which equals to 0.437 molar. What does this tell us? What does molarity tell us? How many moles of our solute, in this case magnesium sulfide, so it's kind of like a powdered solid, I have 0.437 moles of magnesium sulfide per 1 liter of solution. So if I got 1 liter, and this is just mixed in water, and I calculated the exact number of moles of that, there would be 0.437. Anyway, so again, it just tells you how many moles per liter. Now the next one, again, I'm just going to set this up for you because it's a similar problem. If 3.16 grams of copper nitrate is dissolved to make 0.53 molar solution, what is the volume? So you see the molarity. Remember, molarity is moles per liter, or so which is moles, or the amount per volume. So basically what we're going to do is now we're just going to solve for volume. So let's start putting these down. I'll set it up for you. So we have 3.16 grams of, I don't remember what we had, copper nitrate, CuNO3, and what was the molarity? 0.53. Okay, now remember, molarity equals to moles per liter. And it wants us to find the volume. And I think it actually wants it in milliliters, but that's not a big deal. Basically what we're trying to find is liters right here. So we have a molarity, check, check. So start putting into the formula, 0.53. We don't have moles, but we can get it from here. So what we need to do is convert this to moles using the molecular weight. So use the molecular weight per 1 mole. Calculate that. That'll give you the moles. And then all you need to do is search for your liters. And that's it. So I'm just going to set that up for you there. Again, if you have trouble, let me know. But it's the same. It's just applying that molarity is moles per liter. And so either they always have to give you 2 numbers. You're either going to get, molarity in moles and you find liters, or they'll give you molarity in liters and you find moles, or they'll give you moles and liters and you find molarity. So there's 3 different combinations there. They'll give you 2 numbers and you have to solve for 1. Let's look at the last one here. This is a dilution problem. This is similar to the last chart in Lab 1. I think it was in Table 9, maybe? What is the concentration when you dilute 55 milliliters of 6 molar HCl to the final volume 750? Okay. So anytime they say dilution or diluted, some form of dilution or dilute, you're going to use this formula here. M1V1 equals to M2V2. M stands for molarity. V is volume. And you could put that in liters or milliliters. It actually doesn't matter. Okay, so it gives us M1, our first initial molarity is 6. Our first initial volume is 55 milliliters. And our final volume, or I could say volume 2, is 750 milliliters. And they want to know, well, what will the new concentration be? Okay, so what happened here? I have this beaker. I have 6 molar solution in there. Okay, so very concentrated hydrochloric acid. I have 55 milliliters of it in a beaker. Okay, but now I added 750 more milliliters. What is my new molarity? Because I added a lot more water to it, so I diluted it. Okay, so I just plug this in here. M1 is 6, volume 1 is 55. Volume 2, or I don't know molarity 2, so I just put M2. Volume 2 is 750. Okay, now I'm solving for M2, so it'll be 6 times 55 divided by 750, and my new molarity is 0.44 molar. Okay, so again, how do I know to do M1V1 equals M2V2 versus just doing a regular molarity problem? One thing is going to talk about 2 different molarities, but it'll use the word dilution in the problem, some form of dilution. So if I go back to it here, what is the concentration of a solution by diluting? So diluting, dilution, diluted, some form of dilute is in the problem. And you see you're going to get 3 different numbers there. Anyway, so I hope that helps. Let me know if you need any more help.